So in my research group, we use ideas from engineering and mathematics to study the human brain. In engineering, we are very good at building large-scale systems, things like airplanes and power grids, the internet. And we're good at those things because we have a fundamental mathematical understanding of their dynamics, of their physics, of how they behave. What I'm trying to do in my research group is to bring that mathematical thinking to understand how the human brain works. To use equations to try and understand how cells in the brain communicate with each other, how regions in the brain communicate with each other, to allow us to see, hear, and think, to promote our cognitive functions. Because my group is at the intersection of engineering and science and medicine, we're very collaborative. So we work closely with researchers at the Washington University School of Medicine. We currently have collaborations with researchers in neurology and anesthesiology. I also work very closely with basic neuroscientists here at Washington University in the Department of Neuroscience and the Department of Biomedical Engineering. Being able to sort of easily arrange meetings with these collaborators and exchange ideas is something that really helps us to push the frontier of what we're doing. It's fun to work with students who are creative, who bring that creativity and that desire to solving what I believe will be some of the most important problems in our lifetime.
My project in the lab has been studying pediatric patients' EEGs, looking at the brain dynamics. Our collaborators in pediatric neurology came to us with a new pattern that they thought they found. It was correlated with pretty poor outcomes. So one of the things that I've been working on is creating a pipeline to automatically detect when this pattern is found, with the goal of being able to alert physicians when the patients have this so that they can provide better interventions and better treatment and hopefully help these really sick kids.
In my project, we try to analyze how the early sensory networks and information about peripheral stimuli into relevant representations for higher-level brain processing. We are particularly interested in finding out as to how these networks enable detection quickly and accurately at the same time in a combinatorial setup. We are also interested in understanding how behavioral outcomes are interlinked with the information that is provided by these early sensory networks.
So the problem that I'm currently working on is how do we achieve formal mathematical descriptions of the brain? So not just being able to describe a single instance of the brain that we might measure with an fMRI or EEG machine, but actually being able to describe the fundamental rules that govern how the brain works. So in an applied domain, the problem would be how do we determine what sort of extrinsic input to the brain would cause a desired state. So for instance, if we were to deliver electrical stimulation to the brain, can we choose a waveform that will achieve a brain state that we consider to be healthy or at least preferable to the current state in disease?
My current research focus is on training recurrent neural networks to perform cognitive tasks, and then reverse engineering the network to see how the task is performed in that network and try to look into both the dynamics and the structure of the network. We hope that at the end, this project gives us a better view of how the actual brain networks are performing the computation and the cognitive tasks, and how the learning is happening in the brain.